My name is Alexi, and it's my pleasure to introduce Remi Delaporte-Mathurin, who joins us live from Paris. He has a long trajectory in finite element modeling and multiphysics simulations. In fact, during his undergrad studies at the Polytechnical University of Nantes, he developed meshes and multiphysics workflows for radioactive waste containers at the Column Center for Fusion Energy in England. Working towards a Ph.D. in material sciences at the Sorbonne Paris Nord University, he now investigates the influence of helium bubbles on tritium retention in the plasma-facing components of magnetic fusion reactors. As you know, tritium is one of the key ingredients for fusion energy. However, as we learned last week, tritium can be quite an issue of itself. Tritium contamination can reduce the lifetime of the plasma-facing components by causing embrittlement or require extra maintenance in the cooling system. Of course, there are also radioactive concerns which require certain limits on the inventory. Tritium dynamics can be studied in laboratory experiments, but as Remi will show, can also be simulated with thermokinetic models. Without further delays, I will now mute myself and hand over to him. Welcome and enjoy the talk.
All right. Thank you, Alexi, for that nice introduction. I hope you can all hear me well. So yeah, thank you very much for attending. Today we're going to talk about how to track hydrogen in ITER plasma-facing components. So you all know this big guy. This is ITER, and in ITER plasma we'll have deuterium, tritium, and helium. As you can see on that very precise sketch I drawn here, most of the flux will be concentrated on this blue region, which is called the diverter. We're very concerned about tritium in these component in particular. For tritium contamination issues, like you said, Alexi. You can refer to last week's talk from Patrick White, which was about the safety issues. So it's important to notice that in ITER, in a vessel, the maximum quantity of tritium allowed is 700 gram or 1 kilogram, whether you take into account the cryopumps or not. So you have to be very careful with how many tritium is trapped in these components. Second issue is the material embrittlement. I'm gonna talk about that a bit later. And third issue is the plasma performance reduction due to recycling fluxes from this diverter. All right. So what happens when you have plasma wall interactions? So first, you're going to have implantation from the plasma into the material of hydrogen ions. These ions will eventually diffuse from one interstitial site to another, and they can eventually be trapped at defects such as vacancies or even impurities. If their temperature is high enough, they can detrap from these defects and diffuse again. If their temperature is high enough, they can detrap and go back to the surface. If they meet another hydrogen atom, they will recombine into their molecular form and go back into the plasma. So this causes plasma performance reduction because this would lead to plasma cooling. So we don't want that. From a material point of view, plasma wall interaction could lead to blistering at the surface. So you can see these tiny bubbles here. But more importantly, to hydrogen-induced cracks. So you can see here a crack induced by hydrogen implantation, which will obviously reduce the component's lifetime, which is not, again, something that we would like in our tokamaks. So I hope I've convinced you guys that we need to keep track of hydrogen in materials. So we can actually do that by experiments. So for example, the thermodesorption experiment, which consists basically in loading a sample with hydrogen and then heating it at different temperatures. And the measure how much hydrogen atom dissolved from this sample. So you do that for several materials, and you get several spectra like this. So here I'll show you IRFM, tungsten, and beryllium as an example. The thing is, these experiments are not necessarily representative of the full-scale component that we are interested in. So in order to scale up, we need numerical modeling. So how do we model hydrogen transport mathematically? So Magnam and Foster introduced the thermokinetic model a while ago in 1963, and they proposed to separate hydrogen into different populations. So we separate the temporal evolution of the mobile concentration, so the hydrogen that diffuses in the material, and the trap concentration. So in black in this equation, you can see I've put the materials properties we need. So these material properties, we can actually identify them with the experiments I've shown you just before. Some of these properties are highly dependent on temperature. So we're going to need to check the temperature of the sample and the temperature of the component. That's why we have to solve the heat equation as well. So in the heat equation, this one is more common. So the temperature is T in Kelvin, and again we have three materials properties that we need. So namely the density, the heat specific capacity, and the thermal conductivity. So I promise no more equations from now on. Only go back to the cool stuff. So back to our monoblocks problem. As I told you, the plasma stays here, and it strikes the diverter on these two strike points. So in ITER, the diverter is actually made of plenty of tiny bricks that we call monoblocks. So this is a monoblock. There are plenty of them, several thousand actually, and they're made of tungsten mainly, but there's a copper cooling pipe running through them. So from a numerical point of view, this simulation problem is multi-material, multi-dimensional, and multi-physics, because you have to solve the heat transfer equation in that. So which code can we use to simulate hydrogen transport? Well, in fact, we have plenty. You may know TMAP7, that is maybe the most used one, but it's really hard to get the distribution of it. But you have plenty of other codes that have been developed through time. But the thing is, neither of these codes can perform multidimensional and multi-material and multi-physics simulation at the same time. So that's why we need a new code. So we came up with a code named FESTIM, which stands for Finite Element Simulation of Tritium in Materials. FESTIM is based on the finite element methods that we include in the Phoenix project package. It's able to perform 1D, 2D, and 3D simulations. And it's multi-physics, meaning that we solve both the hydrogen transport and the heat transfer equations in it. And like I said, it's able to perform multi-materials simulation. So if you need more info on that code, please refer to our previous paper in nuclear material energy if you need more details. All right, back to our monoblocks problem. So first thing we need is materials property. So we're going to need the trap properties that we talked about earlier. So namely the trap density and the energy of the trap for each material. So the energy of the trap is actually how deep the trap is. So how much energy you need to come out of this trap. So for tungsten, we're going to say a 1 EV trap. For copper, 0.5 EV, and for copper alloy, a 0.9 EV trap. Right. Next thing we need is the boundary conditions. So for hydrogen transport, we're going to first assume that the concentration is imposed at the top surface. So we're going to impose the mobile concentration of hydrogen CM. On the coolant surface here, we're going to assume a molecular recombination into the coolant. For the heat transfer problem, we're going to assume a thermal flux, heat flux at the top surface here that I call phi h, and on the cooling surface, a heat exchange with the coolant. And we're going to assume that every other surface is insulated for simplification purposes. All right, so let's run the simulation and see what happens. So first simulation we run is the thermal behavior one. So we're going to run plenty of thermal simulations, and this is the kind of thermal field we can obtain. So obviously, the higher you get, the closer you get to the top surface, the hotter you get. So, and you're cooler down close to the cooling pipe. So far so good. But we actually want to do that for several heat flux. So we increase the heat flux up to 10 megawatts per meter square, and we measure the average surface temperature at the very top of the monoblock. And we can see that basically it evolves as a linear function of the heat flux. So that will be our direct relation between heat flux and surface temperature for later. All right, I apologize for that poor quality video, but this is the retention field of hydrogen in a monoblock through time. So the retention is actually the sum of the mobile particles and the trapped particles. So that actually all the local concentration of hydrogen in this component. So first thing we notice is that with time, hydrogen penetrates deeper into the monoblock. But second things we notice is that we have a high retention zone appearing here. And that is because in this region, the temperature is quite low. It's closer to the one of the coolant. So we have higher retention in cold regions. With this kind of field, we can integrate the retention over the whole domain in order to get the total inventory of hydrogen in the monoblocks, which is the metric we're interested in. All right, we've done that for several surface conditions. So each point here corresponds to a monoblock simulation, and we made the surface concentration and the surface temperature vary. So I give two examples of the fields we can obtain, and you can see that we can obtain very different fields depending on what surface conditions you put in. So the idea then is to use these plenty of data points and map them into a continuous field. So that's what we did with a machine learning algorithm that enables us to obtain a direct relation between inventory and the surface conditions. So we're very happy with that, because this means that we won't need to do any simulation because these simulations are quite costly, numerically speaking. But thanks to this relation, we don't need that anymore. So we're happy with that. But can this really be applied to our initial problem, which is the diverter? So first, what are the inputs? In the diverter, you have two main targets, which is the inner vertical target and the outer vertical target. And the plasma strikes on two strike points here. The inputs we need is actually the distribution along these targets of the ion energy and the ion flux. And we have this information from codes like SolPS. So here you can clearly see the two strike points where the flux is more important. Right, so we need to obtain the surface temperature and surface concentration as function of these two parameters. So let's start with surface temperature. Because we can obtain the heat flux, and because we have the relation with this we talked about earlier, we can obtain the surface temperature. So first thing we notice is that the surface temperature is roughly, for most of the monoblocks, the surface temperature is close to the one of the coolant. And we have only 2 monoblocks here and here, where the temperature is really high. It's 1100 Kelvin. Okay, so next, the surface concentration. So again, each white circle corresponds to a point of the diverter. For the surface concentration, we actually have a nice analytical formula for that, that links the surface concentration to the incident flux, phi incident here, and to the ion energy and the surface temperature we calculated just before. So one thing that's worth noticing is that, oh, sorry for that. Hang on, there we go. The maximum surface concentration is actually not for the highest ion flux, because for these high fluxes, the temperature is too high, and then it decreases the surface concentration. So the maximum is roughly around 10 power 22 hydrogen per meter square per second. So now that we have the surface concentration and surface temperature, we can feed them to our previously mentioned behavior law that we obtain with our plenty of simulation points. And this gives us what we need, which is the inventory per monoblock as a function of ion energy and ion flux. And again, you can see that the maximum is not necessarily for the highest flux. Right, so we are nearly there. We can have now the inventory per monoblock along the targets, the 2 targets, and we can again see the 2 strike points on the 2 targets. And surprisingly enough, the inventory here decreases at the strike points. This is again due to temperature, because the temperature is higher, then the retention drops locally. So now we need to integrate this onto the whole monoblock, the whole diverter, sorry, in order to have the actual result we need. So we did that, and we noticed that first, the total inventory, the total hydrogen inventory, evolves at square root of time, so power 0.5. So after 10 days of exposure, we roughly reach 2.5 grams of hydrogen in the whole diverter. And after 100 days of exposure, we reach 8 grams of hydrogen. So it's not that much comparing to the actual inner vessel limit of the ITER diverter, which is 1 kilogram or 700 grams if you don't take into account the cryopumps. So we're quite happy with that. All right, let's sum up this a little. So we have simulated hydrogen transport in ITER-like monoblocks with the code name FESTIM. We've performed parametric studies of these monoblocks where we varied heat load, surface temperature, and surface concentration. We've been able to estimate the total inventory of hydrogen in the diverter after 100 days of exposure. And we're quite happy with that because this technique can be applied to other exposure conditions instantaneously. Like I said, we don't have to rerun the whole 600 simulations to do that. We just have to use these behavior law we calculated just before in order to do so. This work's just recently been submitted to Nature Scientific Reports, so stay tuned if you want more details. This leaves some unanswered question, though. For example, what about the beryllium co-deposition onto the monoblocks? Because this is where we expect the most of hydrogen retention to occur. What about the retention in the rest of the first wall? For example, the blankets or the tritium breeding system in ITER. What about retention in dust? We know that we're going to have tungsten dust in the Tokamak. Can these dusts retain hydrogen? What about helium-induced damages? You can have helium bubbles that will maybe increase retention or decrease the retention. We have to work on that as well. And what about the permeation to the coolant? Like I said, tritium contamination to the coolant system is very concerning. So we need to address how much hydrogen goes through and contaminates the coolant. And finally, like I said before, we would like to apply this to other exposure conditions, maybe other tokamaks as well, in order to have a broader idea. Right, that concludes my talk. Thank you very much for your attention. If you have any questions, suggestions, please do ask in the Q&A question or raise your hand.
Thank you very much, Remi. What a great talk. Do we already have a question? In the meanwhile, people warm up their questions. Since you're currently working on the helium problem, would you like to tell us a little bit more about this?
So I was saying helium is a bit different because helium will easily cluster with other helium atom, and it can form into bubbles. So we know that bubbles can form in tungsten, for example, but we need to create new models in order to take into account the interaction between these helium bubbles and the hydrogen retention. So, for example, some models suggest that hydrogen will be trapped at the near surface of these bubbles. Other models suggest that hydrogen will be trapped in secondary defects created by these bubbles, like vacancies or things like that. So we have to figure out what's happening, and we have to figure out will be troubling for fusion application, fusion devices.
And another question I had, which may be a little naive, is when you talk about hydrogen, when you say hydrogen retention, are you talking about tritium? Are you talking about deuterium? Both? Is it? Are there isotopical effects that are relevant?
So that's actually a very good question. In this work, when I talk about hydrogen, I talk about every kind of hydrogen, because this is a conservative assumption. Like I said, we estimated 8 grams of hydrogen isotopes in the monoblocks. We know that it won't be 8 grams of tritium, it will be less, so that's conservative. But yes, there is a isotopical effect. For example, the coefficient diffusion for tritium or for deuterium or for protium is not the same. And you can maybe have some models suggest that hydrogen can interact with another kind of hydrogen inside a vacancy, leading to multi-trapping models, things like that. Yes?
I'd like to ask you, are you examining even molecular effect on surface, or just atomic?
Yeah, so atomic effects is another kind of surface model, right? So the main advantage of this technique is that the surface model, you can actually adapt it to whatever you want, and you can have the same behavior law. So in this work, I only took into account the molecular recombination of two hydrogen at the surface. If that answers the question.
Yeah, sorry, it seems to be that I missed this point. Sorry.
Not at all. We have a question from Lei.
Yes, can you hear me?
Yes, nice and clear.
Thank you. It's a very interesting talk. And you have mentioned that you have use some machine learning techniques, but you have speak very fast. Could you please say a little bit more about it and which kind of machine learning technique you used?
Can you all see my screen here?
Yes.
Yeah, great. So the machine learning algorithm I use is actually a Gaussian regression process, and we use that instead of a classical interpolation because this gives us a metric, a standard deviation of the interpolated results. So that's the algorithm we used.
And what kind of training data you have used? And
so the training data is actually the gray crosses you can see here.
Mm-hmm. Okay. And how many training points
there are in this work we have 600 points, a bit more, I guess. But we tested the algorithm with a bit less, and it works pretty fine as well.
Yeah, I mean, for me, 600 it's not so much, and how can you be sure that this can be used to the data that haven't been included in the training set? Because you said that you don't need to run the other 600 simulations anymore, and you wait after you get the.
Basically, what I meant is that if we want to have information on monoblocks in that range, because we use that regression process, and we know that roughly everywhere the standard deviation is acceptable, we don't need to have more data points, data training points, in order to get a better accuracy. That's what I meant.
Okay. And do you use some your own code, or you use MATLAB, some kind of things?
Yeah, I'm not a mathematician really. So I use a package named inference tools. That it's kind of a black box to me really, but
okay.
No, that's not my own code.
Is there a website about your finite element code?
So the FESTIM is not open source, but you can refer to our previously published paper if you want more details about it.
Yeah, I found you have shown it in the slide, but I haven't managed to write it down. Could you please write it in the chat? Then I can try to find it.
In fact,
I've put my email, my contact details here. Don't hesitate to drop me an email, and we can maybe talk about that.
Okay.
More details later. Or
we will also
LinkedIn
include the links to the papers. Maybe Remi, if you can provide it to us, we'll include them in the
I mean that. Yeah. Thank you very much.
Thank you.
Okay, are there any more questions from the audience? I think I see one here from Hendrik.
Why do you say it?
In the participants box. I can actually.
Can you
Hendrik,
hear me?
are you able to? Yeah, great.
Yeah, great.
Hi there. This might be a little bit off topic, so stop me if you've answered this in a previous presentation, but I was just wondering how this hydrogen in the tungsten affects the overall performance of the Tokamak. I guess I'm kind of wondering how much hydrogen is I think, did you call it a retainer or the blocks? How much can they absorb, and how long can we keep them there without replacing them?
So from the, are you speaking on the material point of view or on the plasma point of view?
Both. Now that you mention it, both. So
I'm not a plasma physicist, so I'm not really an expert in that. But what's happening is that when two hydrogen atoms recombine, they're going back into the plasma. But the thing is, they're not as energetic as they were when they came in. So it makes which we call a recycling flux, and this cools down the plasma. So it cools down the scrape-off layer of the plasma, and this is what reduces the performances. From the material point of view, to be honest, I don't really know how much hydrogen can take before it breaks down, or for how long we have to use them before replacing them or anything. That's a very good question.
Yeah, because you were mentioning the 8 grams after 100 days, and that's, I'm assuming, 100 days of just constant exposure.
Yeah. So the scenario here is purely theoretical. In ITER, you won't have 100 days of exposure continuously. It's just to have an idea. So yeah, future work will include studying cycling effects, for example.
Oh, okay.
But the 8 gram thing is not from a material point of view. It's just a safety limit in case of a loss of vacuum accident, for example, in order to limit the risk of release into the environment of tritium.
Oh, I see. Sounds good. Thank you.
Thank you.
So this concludes our online Q&A session. I will now stop the recording and thank everybody for joining us today.
Thank you all.